Hello and welcome to Empowered Learning. This video will be about the study of the three-dimensional coordinate system. And so our goal here is to get familiar with what the three-dimensional coordinate system is, some basic properties about it, and we will also talk about how to do basic things such as find the distance in between 2 points in a 3D system. We'll also talk about what the general or standard equation for a sphere is. And essentially a sphere is just a three-dimensional circle. Okay, so we're going to look at all those things, and then in the latter part of this video, we'll do several examples of taking those concepts and definitions that we'll learn to be able to practically apply. So the picture that you see here is the convention that we're going to use for the three-dimensional coordinate system. There are several conventions, but this will be the one that we'll use. And so we basically say that this is the three-dimensional coordinate system that goes along with the right-hand rule. And so that's why you see the person's right hand there. And so for this particular convention, we are looking at the z-axis here. So our z-axis is going to be pointing up in the air, so pointing up vertically. So we see that here where it's pointing up vertically, okay? We have other conventions where, let's say, the left-hand rule would actually have the z-axis pointing downward. The positive z-axis would be considered going down instead of up. We have other conventions where the z-axis, if you can imagine it, would be kind of where the x-axis is, and that axis would be shooting out of the page. If we're using the right-hand rule where the z-axis is laying down like this, or we could have it shooting through the page in this direction. So my point is that there are several different conventions that we can use, depending upon the application of what you're going to be using the 3D coordinate system for. It may make sense to use the right-hand rule where the z-axis is shooting out of the page towards you. Other times it may make sense for you to let the z-axis be pointing down vertically and let that be the positive z-axis. So it really just depends. For this video, though, the convention that you see here will be the convention that I will use on all problems. And so the other thing here that we want to mention is that, of course, our points in a 3D coordinate system are ordered triples, okay? And of course, they're called ordered triples because order actually matters here. So the x coordinate has to come before the y coordinate, and the y coordinate has to come before the z coordinate, okay? And notice here that since we have a three-dimensional coordinate system here, we're also going to have several different planes and regions, and depending upon the region of points that we look at, we may have a region, if we looked at it as a solid, that would actually have some volume, okay? So again, we'll look at all those things. So I'll go ahead and skip down here because I think the rest of this you can actually see. I guess the only other thing I want to mention here is that, of course, the x-axis, points that are on the x-axis will look like this. The x-coordinate would be some real number. Y and z coordinates will be 0. Of course, for the y-axis, the y-coordinate will be the only one that is non-zero. And of course, for the z-axis, points on that, only the z-coordinate will be non-zero. And notice here that if we look at the top of this little box here, and this is something that is very important that we'll utilize later on, is that the top of this box is considered to be what we call a plane. And we'll talk about planes here in a little bit, but basically think of a plane as like a sheet of paper, an infinitely long sheet of paper. And so if we have a set of points that are actually on this sheet of paper or a plane, then we know in this instance for this particular, the top of the box here, we know that the z coordinate is going to be constant, okay? If we were looking at this particular side of this box or sheet of paper, then the X coordinates would be constant. And we can easily see that because here with the X coordinates, notice that right here where I'm kind of making this mark here, that is X equals some value. And for this whole entire side here, all of the X coordinates are going to be the same. Now, Y coordinates, Z coordinates may be different, but the X coordinates will be the same. And just like up here at the top, we know that the X and Y coordinates for this part here could be anything, but the Z coordinate would have to be the same. Okay. And so again, we'll use that knowledge later on to help us to be able to do some of the problems that we do. Now, the formal name for the coordinate system that we are going to be studying here is called the Cartesian or rectangular coordinate system, of course, in 3D. But there are other three-dimensional coordinate systems that we look at. The two that are probably the most popular, other than this, the one that we're studying here, is called the spherical and cylindrical coordinate systems. We won't go into detail on those in this particular video. But if you're studying the third sequence in the calculus sequence, known as Cal C or Calc 3, you will start to study those particular coordinate systems and see how certain equations, in particularly differential equations, are modeled by that. So, for instance, the wave equation, just studying waves in general, magnetic fields, all that stuff. We could model with either spherical or cylindrical coordinates. Okay, and so this is an example of what those coordinate systems look like. Out of these three, of course, the Cartesian one is the easiest one to deal with, so that's why we're starting with that. And again, if you are in a Cal C course or a Cal 3 course, you'll eventually talk about these two. Okay. So now what we need to do is sort of dissect what our three-dimensional space looks like. And so just like we know we have in 2 dimensions, the XY plane, we have our plane divided up into 4 quadrants, just like we have that in the three-dimensional coordinate system, or in 3D space. We are going to have octants, or basically 8 different regions instead of just 4. Okay, and so this picture that you see here is a picture of those 8. Now, out of all of these, the main thing that we need to know is in each of these regions within this 3D space, each octant has its own profile as far as what the points look like that are in it. The only octant that is sort of set in stone as, hey, you label this octant this way, is going to be octant number 1. And that's the one where the X, Y, and Z coordinates are all positive. So we would call this particular region of points here octant number 1. Now, for the rest of these, it really just kind of depends on how you feel comfortable labeling them. But there is no standard convention for labeling the rest of the octants. Okay, unlike how it is here with the XY plane in 2 dimension, we normally do go counterclockwise to be able to label those quadrants. Okay, now again, you can think of this 3D space as just a box with some dividers in it, and what we've done is divided the volume that's in the box into 8 equally spaced areas. And so that's another way that you can think of these octants. So here you see that I'm doing a comparison here with the XY plane that is basically 2D space along with the 3-dimensional space. And so here again, you see that we have our 4 quadrants and the corresponding points that go there. And of course our 8 octants here and the corresponding profile of points that go there. Okay. And again, I mentioned here that on the octant 1, this is the only one where it has a formal label. The rest of them, we could have rearranged these numbers in any way we want. Okay, so now what we need to do is delve a little deeper into this 3D coordinate system and start to see or start to study certain pieces of it. And so what we're going to do now is kind of look at, well, what are the two-dimensional pieces of this three-dimensional coordinate system, okay? And so one way that we could, I guess an alternative way that we could think about this particular three-dimensional coordinate system is we could think of building this coordinate system by taking infinitely long sheets of paper. And let's say we had a bunch of them. We would take an infinite amount of those sheets, and we could sort of orient them this way. Okay. And so what I mean by that is the sheets are basically going from north to south. Okay. And we're stacking them in such a way to where let's say if you were to stack some books on a desk, starting with the first book closest to you, and then you would stack books behind it. That's kind of how this would go. Okay. And actually, I probably shouldn't say north-south here, because that's actually for another plane. So again, I think a better way of saying this is for this one, this is going to be back and forth. Okay. So, or front back. We'll do it that way. Yeah, that's probably a better way to do it. So if we stack those infinitely long sheets of paper from front to back, that would cover what's called the YZ plane and all of the planes that are parallel to it. If we stacked from north to south, then that would take care of what's called the XY plane, which is what we're familiar with already in 2 dimension. So take care of that and all of the planes that are parallel to that. And then of course, here, if we went from left to right, then we could orient those 3 sheets of paper, that way and stack those. And if we imagine that these sheets of paper are all permeable, meaning that we could have things go through them, intersect them without changing the shape of that actual sheet of paper or the sheet of paper that it is, I guess, intersected with, then what we essentially have is this big volume box. Okay. Now, the reason I'm going through explaining this in that way is that one of the things that we are going to do in this particular video is describe regions of points based upon what plane they are in. And so what we need to know is basic things about planes to be able to do that. So if we think of this 3-dimensional coordinate system as a bunch of planes, or as I like to call them, infinitely long, wide sheets of paper with infinitesimal thickness, going in those 3 directions that I mentioned here, meaning from front to back, north to south, or in east to west, or left to right. Okay. So if we look at that way, then we see that our 3-dimensional coordinate system is just an amalgamation of a bunch of planes kind of being smushed together. Okay. So in thinking about it this way, we now have the tools to be able to describe regions of points that are on planes in a more effective and efficient way. Okay. And so one of the things that we want to do now is take a look at, well, what are going to be some of the basic properties of these planes? What are our fundamental planes, and how do we describe planes that are a variation of a theme off of the fundamental planes? All right, so let's take first things first. So the first thing that we want to do is define what our fundamental planes are. And as you can see here, those three fundamental planes are going to be the XY plane, the YZ plane, and the XZ plane. Okay. Now, if we look at the XY plane, notice that the XY plane is intersecting. It has this point here at the origin. Okay, so I'll say it like that. So because of that, one of the things that we know is that for the XY plane, it must always be true that the Z coordinate will be 0. Okay. Now notice that that's easy to remember because in the XY plane, the one letter that we don't mention is Z. So if we have the XY plane and we say, well, what are the Z coordinates? Then of course, for the XY plane is going to be Z is equal to 0. Okay. Thus for the YZ plane, we know that all X coordinates must be 0. And for the XZ plane, we know that all the Y coordinates must be 0. Okay. Now, it is important to note that these are the only three planes that are defined by name like that. Okay. So in other words, the XY plane is by definition the plane of all points that look like this. Okay. X could be any real number, Y could be any real number, and of course the Z coordinate would be 0. If we were considering a plane that was parallel to the XY plane, so let's say I had a plane that was way up here that looked like this, and that plane is parallel to the XY plane here, we would not also call this an XY plane. Okay, this would not be an XY plane. What we would have to do in that case is describe that plane by the Z coordinates Z coordinate that it must have. Okay, so let's say, for instance, way up here, we know that all of the Z coordinates have to be 20. Okay, so in three-dimensional space, when we say we have the plane Z equals 20, we know that that is a plane that looks just like the XY plane down here, but it's shifted up 20 units. Okay, so same exact plane, but all the points are being shifted upwards 20 units. And so that's how we would describe planes, that particular plane in this three-dimensional coordinate system. Okay. So similarly here, and I'm going to erase and then do another example so you kind of get an idea of how this works. All right, so now that I've cleared some things here, let's say I wanted the plane or the collection or set of points that are going to be similar to the ones that are on the YZ plane, but they are, but this plane is shifted 2 units up on the x-axis. Okay, so in that case, what I would have at, let's say, x equals 2, I would have a plane that would look something like this. And here, all the points on this particular plane would have in common that its x coordinate would be 2. Okay, so all the points on this plane would look something like this. Doesn't matter what y and z are, but it matters that, of course, 2 is always the x coordinate. And this particular plane here will be parallel to the YZ plane. Okay, so it is the YZ plane just shifted up 2 units. I guess 2 units up on the Z axis. Okay, and of course, with the XZ plane, I know that I would describe planes in terms of y equals a number for that. If I wanted to, let's say that y is equal to -2, then let's say, let me erase a little bit more of this here. So let's say back here, I have y is equal to -2. Then I would have a plane that kind of looks like this. And this plane here would be parallel to that one, okay? And of course, the points in this plane would look like x, -2z, okay? All right, so that's one of the main things that we need to know. Whenever we are describing planes, we're either going to be describing planes in terms of those set of points being either parallel to either the xy plane, yz plane, or xz plane. Another way that we'll describe them is a set of points that are on a plane that are perpendicular to a certain axis, okay? So I'm going to erase again, and then we're going to talk about looking at, well, considering what plane is perpendicular to what axis. All right, so we know that the word perpendicular means that the two objects that we're considering just intersect each other at a 90-degree angle, okay? Now, in general, we know that the x-axis, the y-axis, and the z-axis are all themselves perpendicular to each other, okay? We know that because x-axis is perpendicular to the z-axis, x-axis is perpendicular to the y-axis, and of course, z-axis is perpendicular to the y-axis. We know that. So what we're concerned about here is how do we look at this in terms of planes, okay? So let's take the xy plane first, since that's the one that we're used to dealing with here. So notice that the xy plane lays horizontal. So what I need to pick is an axis that would intersect this horizontal sheet of paper vertically. And of course, the only one that does that is the z-axis. Because if you notice, the z-axis is the one that kind of goes down through here like this, okay? So we know that the xy plane here will be perpendicular to the z-axis, okay? And so one of the ways that we could describe a plane is, hey, we want a plane that's going to be so-and-so and perpendicular to the z-axis, okay? Whenever we say a plane is going to be perpendicular to the z-axis, we automatically know it's going to be a plane that looks like the xy plane, meaning it's going to be a plane that's going to lay flat horizontally and go from east to west or west to east, depending on how you want to look at that, okay? Now, if we're not talking about the xy plane specifically, let's say we're talking about a plane that's 1 unit up on the z-axis, then the plane z equals 1 would be the plane that is parallel to the xy plane, but also perpendicular to the z-axis, okay? So if we think about that way and then apply it to the other planes here, so we just said here that the xy plane is going to be perpendicular to the z-axis. And of course, notice that z is the letter that's missing here. So if we were talking about the yz plane, then of course you would think that that would be perpendicular to the x-axis if we follow the logic there, okay? If we look at the yz plane, again here, we want to know the yz plane is vertical, and we want the plane that is going to intersect it that's horizontal. And of course, the x-axis is that axis, so that makes sense, okay? And of course, the xz plane that should be perpendicular to the y-axis. And of course, XZ plane here is also standing vertically. So we need the plane that's going to intersect that horizontally. And of course, the y-axis is the one that does that. Okay. So these are also very important properties that we need to know about these planes and axes. All right. So in summary here, what do we need to know about these planes? So the first thing that we know here is that the XY plane, we know that it's going to be perpendicular to the Z-axis. So we know that that's always going to be true here. Of course, with the XY plane, we know that the X and Y coordinates can be anything, meaning any real number. And of course, by definition, the Z coordinate would have to be 0. Similarly, for the YZ plane, we know that the YZ plane will be perpendicular to the X-axis. Our YZ coordinates can be any real number, but of course our X coordinate would always have to be 0. And finally, for the XZ plane, we know that the XZ plane is going to be perpendicular to the Y-axis. And again, X and Z coordinates can be any real number, but our Y coordinate would have to be 0. And again, if we describe any plane that is going to be parallel to any of these planes, we would have to describe them in terms of, for the XZ plane, it'll have to be Y is equal to whatever number that's there. For the YZ plane, it'll have to be X is equal to whatever number would work. And for the XY plane, it would have to be Z is equal to whatever number that works. And what I mean by whatever number that works is if we're looking at that plane that's parallel to one of these, we know that either the Z coordinate in the XY plane case would always have to be the same for every point that's on that sheet of paper. In the YZ plane, we know that the X coordinates would have to be the same on that sheet of paper. And for the XZ plane, we know that any plane that's parallel to it will have to have the same Y coordinates on it. Okay. All right. So another thing that I want to illuminate, and I actually mentioned this before, but I didn't complete my statement on it, so I'm going to go ahead and do it now. Notice that all three of these fundamental planes that we've been studying all have the point 0, 0 in it. And another way of saying that is that all three of those planes contain the point 0, 0, 0, or all those planes contain the origin, or they intersect that point. Okay. Now, the reason why I mentioned that is because this is the reason why for the XY plane, Z has to be 0. And for the YZ plane, X has to be 0. And for the XZ plane, Y has to be 0. Part of the reason is it has all three of those planes share that same point. Okay. For all other planes, though, like I've been saying before, we would have to use some other way of being able to describe what's going on with that plane to be able to identify it properly. And we know that at a minimum, we would have to know what is going to be the X, Y, or Z coordinate that must be constant for that particular plane. And it would also be very helpful to know if we knew a specific point that was going to be on that particular plane. Now, we're going to see that sometimes we may need more information, but at a minimum, we're going to need that. Okay. And on the next thing I'm going to show you here is going to be 2 examples. One where we have enough information, another example where we need more information. All right, so for our first example here, if we talk about what is the set of all points that satisfy x equals -1 in 3D space, we know that that's just a collection of points where our y and z coordinates can be anything. Okay, so y and z can be any real number, and so that's the fancy way that we write that. But of course, we know our x coordinates will always have to be a -1, okay? And so here, what we say is that in 3D space, this is the plane x equals -1. And you'll notice that in this video, I will often say the plane x equals -1, because if we were working in 2D space, we know that this would be a vertical line, okay? So since we're working in 3D space, we need to make that distinction. In 2D space, x equals -1 is a vertical line. In 3D space, x equals -1 is a plane, okay? All right, and so in this case, if I wanted to describe all the points that have the same x coordinate of -1, I could just call the plane x equals -1, and that's all I have to say. So for our next example, to see an example of where we may need some more information, we know that the point 2, -1, 4 could be on any one of these three planes here. It could be on the plane x equals 2, y equals -1, or z equals 4, okay? We know that that point could be on there. Now, the thing is, we need to figure out, well, specifically, which plane do we want? And depending upon how we describe that plane would tell us which one we would want. And we need to be judicious in actually doing that description. So one very easy way to describe that we want the plane x equals -2 is to say that we want the plane with this same point on it, but we want the plane to be perpendicular to the x-axis, okay? When we make that distinction, it makes it pretty easy when we look at this visually to know that we're actually talking about the plane x equals 2. And so I'm going to show you a visual depiction of what this problem would look like so you can see what I'm saying. So if we look at the figure that figure A that we have here, notice that I have a portion of the plane x equals 2 drawn, and I have a portion of it only because theoretically this plane extends to the left and the right forever and ever, and also extends up and down forever and ever. But I wanted to draw enough of it so that you got an idea of what it looks like, okay? So here, notice that this particular plane here, if we look in comparison to the x-axis here, let's say I had another point here, notice that this plane or this sheet of paper is standing on top of the x-axis at a 90-degree angle. So of course, that plane is intersecting the x-axis at a 90-degree angle, or it's perpendicular to it, okay? Now, this would be the only plane that would do that and have this point here, because notice that every point that is in this particular plane has to have an x-coordinate of 2, okay? And so in order to ensure that you get that point 2, -1, 4, you would have to pick the plane or the big sheet of paper that has all x-coordinates 2 on it, okay? So this is a very succinct and concise way to be able to say, hey, this is the plane that we want. Now, as a side note to this, let's say we described this differently, okay? So let's say now we want the plane that still has this point in it, but now we say instead of it being perpendicular to the x-axis, let's say that I want it to be parallel to the y-axis, okay? If I describe it this way, then it's a bit more ambiguous to know what plane I'm talking about, and I'll explain why. So first, we know that this particular plane here is parallel to the y-axis, okay? And so we know that because this same plane is parallel to the YZ plane, okay? And if you remember, the YZ plane is just the plane that basically, I'll say, intersects through the y-axis going from north to south. Okay, and I'm going to draw that so that you could see what that looks like here. So this plane would look something like this. Okay. Oops. Yeah. Let's move that. Plane would look something to the effect of this. Okay. So this, in effect, is your YZ plane. Okay. And of course, your YZ plane and the plane x equals 2 here, these planes are both parallel to one another. Okay. Now, notice that the reason why this is ambiguous is because this point can also lie on another plane that's horizontal. Okay. To be specific, I'm going to use this as a guide here, but I'm going to draw a plane that is horizontal to this one as well. So if I draw this plane, draw through here like that. Notice that this plane that I'm drawing in red is also another plane, but this plane is parallel to the XY plane, and it also contains that point 2, -1, 4. And so my point here is that if I describe the plane that I want in terms of saying it's going to be parallel to a particular axis, that's going to be harder to pinpoint. Okay, so I would need some extra information about this particular plane that I'm looking for in order to pinpoint it and say that yes, it's actually the plane x equals 2. Okay, if I was to ask this question, my point is, if I ask this question, or if I say, hey, identify the plane that has these properties, I actually have 2 that could actually satisfy that. And I don't know which specific one that I'm talking about. However, if I talk about it the way that I originally did, as give me the plane that has this point 2, -1, 4, and it is perpendicular to the x-axis, then there's only one choice. Okay, and hopefully that's clear. All right, so hopefully now you see why x equals 2, that particular plane would be the only choice for this example here. If I go to this next example, let's say we have the same point 2, -1, 4, but now we say that the plane in question is perpendicular to the y-axis, then of course y equals 1 would be that choice now. Okay, and so again, if we go to another visualization of what we're talking about, we'll clearly see that. So this is a drawing of figure B, which is basically saying, hey, I want the plane that is going to have the point 2, -1, 4. But in this case, this plane is going to be perpendicular to the y-axis. And again, here, if I was to take just another random point, let's say right here, and I could see here that that plane and the y-axis do intersect each other at a 90-degree angle. Okay, so it's real easy to see why the plane y equals -1 here would actually be the best way to describe this particular plane, given the way that we described it. Now, please don't get confused here with what I have right here. The line y equals 1. This particular line in 2D space is the horizontal line y equals 1. That is true. But when we talk about 3D space, in 3D, this is the plane y equals -1. Okay. All right, so we are just about at the point where we're actually going to go over many of the examples. Before we do that, though, we need to talk about the concept of finding the distance in between 2 points in 3D space, and we need to cover what the standard form of an equation of a sphere is. And again, a sphere is just a three-dimensional circle, okay? So I have this picture here just to show you that our goal here is to be able to find out the distance in between these 2 points. And essentially all we really need is this triangle here to do it. Of course, this other triangle that's here, we need that so that we'll know what the hypotenuse of it is so that we can use that distance there. But we know that the hypotenuse of this real thick line that I'm drawing here is just going to be square root of, let me write that correctly, square root of x2 minus x1 squared plus y2 minus y1 quantity squared. Okay, so that's what that ends up being. And then of course, here all we need is the difference in vertical. And of course, when we actually work that all out, it ends up being this formula that you see down here. Okay. And so just like finding the distance in between 2 points in 2D space, we just have another coordinate to consider. That's the only thing really different about it. The standard equation of a sphere, if you can remember the general or standard form for equation of a circle, not the general, the standard form is this, where we know that the center of the circle is here and r is the radius. Well, the equation of a sphere has that same flavor to it. Of course, the center now is going to be an ordered triple instead of an ordered pair, and the radius is going to be able to emanate out not only in one direction but several. Okay. And so if we look at the formula for that, it just ends up being this here. Okay. And so where this particular formula comes from, if you remember, there is a general form for a conic section. If you remember, a conic section is essentially two cones that are kind of have their apexes kind of, you know, pointing against each other, and we make slices of those cones. Okay. Now, the point in saying that is that we have a long general formula for it, and looking at that formula, it's kind of hard to tell if we're looking at an equation of a circle, a point, a line, a parabola, hyperbola, whatever. But when we rewrite the conic section equations in standard form, and of course make some assumptions, then we know whenever we're talking about a circle versus a hyperbola versus an ellipse, you know, versus a point, whatever. Okay. So my point in saying all that is that there is a three-dimensional version of that particular conic section equation. We're basically just implementing in the z coordinate, and then once we do that, if we did the same sort of thing with that to find that we would do for the equation of a circle with that three-dimensional version of the conic section equation, what we would end up with is this equation here. So without going into all the gory details, that's how we would come up with that. Now, now that we've kind of got everything that we need, I'm going to go ahead and do several examples here of how to work these problems. And I'm actually going to do that in another video, since this one has gotten kind of long. We got the basics now, so let's go ahead and do those examples. And I'll see you in the next video.